Well, welcome to this presentation. It's scheduled for an hour. So this is kicked off because of part of the Buckinghamshire Hidden History initiative, and also coincides with the 80th anniversary of Colossus running its first official job on the 5th of February 1944. So I will also hint at another anniversary, which is pertinent as well to some of the exhibits we've got in the museum, so that'll come later. So the idea is to look at Colossus, but you can't just take Colossus just simply out of context. We need to understand broadly why it's there. So we'll go back to some basics to start with. And starting out, really, what about Bletchley Park? Why on earth was Bletchley Park chosen? Well, the park originally was quite large, something like 500 odd acres, 600 acres. And it was owned by the Leon family as a country retreat. Fanny Leon, the last surviving person who was interested in it, let's put it that way, died in 1937, and it passed into the hands of Hubert Faulkner, who was a property developer. However, before it could be bulldozed, for that time, it passed into the hands of the government for at least 25 acres or so, for £6,000 in 1938, and that was under the auspices of what became known as Captain Ridley's Shooting Party, cover name, which then became the wartime home for what is laughingly called, or used to be jokingly called, the Golf Chess Society, correctly, the government code and decipher school. Also, it was used by what will become SOE. Interestingly, by way of distancing its operations from Woolwich Arsenal, which was colloquially known at the time in the early days of the Department for Bangs and Whistles, as I understand it. This is one of the little snippets that I picked up from Len on one of the calls the other day. So if we're interested in that, I'm sure Len can, towards the end of things, can actually give us a few more ins and outs of that. SOE was perhaps regarded as not quite playing cricket by the Woolwich Arsenal people. So they set up shop in what would become the Bletchley Park complex. Bletchley Park is also well served for communications, north, south, east and west, on rail and telecommunications. Fenny Stratford's about a mile or so away from the site. It's a major flexibility point. It still is to some extent. It was a repeater station for telegraphy traffic, for telegraphy circuits, and regarded as a relatively safe distance from London. So there's pretty well published kind of context as to why Bletchley Park was chosen as a site for the site of GCCS during wartime. Okay, so let's set the scene a little bit and look at a few challenges and solutions and the code breaking aspects of their operations. This is going to be pretty well centered around Colossus, although I've got a picture of the bomb machine up here. But let's get some context. There are some significant achievements in cryptology, call it what you will, at the site. Industrialized processes, managing intelligence, source and product. It was a concentrated effort in this location, and there was wholesale use of mechanization, largely using established suppliers. For example, the British Tabulating Machine Company, and the product of this gentleman over here. This talk is not about Enigma, but this is Harold Keane, BTM, Chief Engineer of BTM, who was responsible for the physical design of the bomb machine. A very successful code-breaking tool used in finding machine settings for the Enigma encryption device. Other government departments also were involved in the output, not necessarily working on site here, but you've got the GPO who were working on site, the Telecom Research Establishment, Radar Research Establishment also down at Malvern, and their resources were drawn upon. There was also the novel application of what would have been regarded at the time as being untrusted technology. And lastly, my favourite bit about this is the final outcome really was, or for me at least, a cherry on the cake. was a zero-knowledge statistical attack on a cipher system. By zero knowledge, I mean no requirement to know what the content of the message was, other than the fact it was a particular language rather than plain text originating in a particular language. And compare that to the Enigma process, which relied on, and was totally reliant on an accurate known plain text attack. In other words, an accurate guess at what was the content of the message. And the larger the guess, the better. So these are kind of groundbreaking in the field of cryptology. There was also a well-established process, the who, where, why, what, and how of signals intelligence. Picking up the Colossus story, we're looking at traffic here, intercepted at Knockholt down in Kent. Knockholt was the focal point for reception of what became known as fish traffic, fish being teleprinter traffic, the code name given to or collectively given to teleprinter traffic. It arrived in Knockholt somewhere in 1941-42, having been kind of piecemeal monitored by the likes of Denmark Hill, for example, and prior to that, very, very early days in Cable Fern on the Kent coast, in a small way, pretty much one man and his dog type operations, those smaller ones. It was industrialised at Knockholt, and the whole site there grew to something like 160 or so acres of herring farms. The irony there for me is that Knockholt is no more than a few miles in any particular direction from strategic targets like Biggin Hill and Hawkinge and those sort of places that were active airfields during the Second World War. But to my knowledge, I don't think Knockholt was ever directly hit, which is remarkable considering the large rhombic area arrays there, something like 80 feet high. So it's got to be. I would imagine it must have been visible to some extent from the height the enemy was flying over. Those signals sent to two organisations, the Testery, occupied by Ralph Tester, and Max Newman's Newmanry outfit, and they're collectively trying to find settings that were used on the particular machine we're targeting here, which is the Lorenz-encrypted. More of which in a moment. The output from those would be part of my Heart 3 and then out to dissemination down to the various points that you're going to take that strategic information. This is it's a different quality of information really from the Enigma decrypts. It's very much strategic information, long messages, battle plans, that sort of thing, whereas the Enigma decrypts were largely disseminated through the special liaison units operated by Fred Winterbottom, who went on to annoy the hell out of the government by publishing the Enigma, still the ultra secret, in the early 1970s. So we are focusing on Colossus at the moment. So that's broadly the process. Some words about mechanization. The man pictured down the bottom here is Max Newman, who prior to Second World War was actually Alan Turing's tutor at Cambridge. And he was commissioned to set up an organisation which became known as the Newmanry, which was concerned with the mechanisation of process. Some of the machines they created was Robinson, short Heath Robinson, which used to convey cipher message punch paper tape with possible key tapes. Miles, Mrs. Miles, sometimes known as, which read one or more paper tapes. In fact, I think Mrs. Miles was named after a lady who had quads. And there were 4 tape readers on this, and it could produce an output tape from combining information from a number of inputs. The device called Dragon, which was dragging cribs or known plain text, looking for K-will positions, actually not looking for cribs. Actually, this is what the text says, but it's actually not quite right, that statement. It's actually testing cribs to see whether they're valid, and to therefore be able to expand plain text out, having already found K-wheel positions. There was a story I was told, I don't know, it would need citation, that the Dragon machine was developed on both sides of the Atlantic. The Americans had a go at creating a Dragon, which was shipped over to the UK, and it was shipped apparently in a very, very high quality wooden box. the sergeant who was concerned with setting the thing up took some time to set the thing up. It was a very noisy thing, from what I understand it, this cryptographer, and came in for some criticism from the UK contingent of code breakers on Bletchley Park, who, when questioned, well, where's your equipment then? Well, it's over there. Well, can I hear it working? And they would say, well, it is working. It's just quiet. It doesn't make the racket yours does. Which, well, at which point the story goes, again, requires citation, the poor American hapless sergeant packed his gear up. Well, he's tried to. He couldn't find the box because it had been filched because of the high quality wood. Much of the wood had been filched to make furniture and the like. So, but I don't think that there's not a lot of credence to that story, but it's a nice story nonetheless. Other machines, Proteus, Aquarius, Tully, for example. Well, Tully we will talk about because that's crucial to the Lorenz story. And the most complex and the most multi-purpose rule breaking and setting machine, Colossus, at the final end of that story. So this is pretty much all down to Max Newman, and without his efforts and the efforts of his team, things would have carried on pretty darn slowly. So let's have a look at the network. Lorenz, the network being mapped out. This is ripped off from the picture in the Colossus gallery that actually was in the computing. It shows you the extent of the network, largely centered on Berlin, but also with another center to the east in Königsberg. And it's a widespread network, as you can see. It's going as far east as eastern Ukraine, practically to the Russian border, way down to Athens, Rome, and the west coast of France, Paris, for example. So this is a wide-ranging network, but not as many nodes on it as the Enigma networks in their varying forms would have taken. So these are teleprinter connections, long-distance radio connections, and of course we're monitoring it over here in Knockholt, which is nowhere near line of sight. So there's a technical difficulty in actually monitoring, let's say, traffic way over here in eastern Ukraine, and getting reliable copy over here in Knockholt is quite a feat. So we have to admire the technical prowess of the interception stations in getting reliable copy up to a point. Obviously, it's not going to be perfect. But masses of information was something 170,000 messages, I think, from memory is the number of them were actually intercepted, not all of which would have been complete, and not all of which would have resulted in successful read. But nonetheless, that's a lot of work going on, given the technology of the time. And you'll notice these are all got allocated fish names. There's an interesting juxtaposition there. Fish is the code word that the Brits gave to teleprinted traffic, and the Germans called it Zegerfish, swordfish, which is a bit too much of a coincidence in my book. I don't know who's having a joke at whose expense there, maybe, or maybe it is a coincidence. That I don't know. Perhaps somebody can fill me in on that one. So what's the challenge then? The path leads to Colossus. Well, we're looking at Lorenz SZ40 in 1940 and the 42 model in 1942. It was subject to some modifications in its lifetime to attempt to improve the ciphering technique. But the basic machine is the Lorenz SZ40. It's a stream ciphering device, as contrast to Enigma, which is a substitution cipher. It hinges around John Tilton's break and Bill Tutt's work in reverse engineering the machine from that single break. That was on the 30th of August in 1941, when a message was transmitted between Vienna, we think Vienna and Athens. It may have originated in Berlin, but it doesn't much matter. It was repeated. It was repeated using the same machine settings, and this is a fatal cryptographic error, particularly if you then go on to ensure that the two messages are different. So the net result was that we had two messages, quite long messages, in the order of 4,000 characters long, which were transmitted with the same key settings. Now, for an additive or a stream cipher, that is a fatal cryptographic error. and it enabled John Tillman to read both messages and extract the 4,000 characters of key by means of about 11 days or so of work. So not a trivial feat by any means. But nonetheless, this is the break that gives us the edge. Bill Tutt then was charged with finding some sense out of 4,000 random-looking letters, and his process was really back to basics. Basic reasoning, I guess, putting myself in his position would be, there's no point in looking at the letters. They are truly random. There are no patterns to the letters, no predictability in the letter sequences. But the thinking is, because these letters are made up of 5-bit code, each one made a 5-bit code, the International Telegraphy Alphabet, 1 to 2, and therefore those bit structures are being modified by a machine with wheels in it. And those wheels must have some periodicity, and it must be a finite period of the order of 30, 40, 50, 60, typical machine like that. So it ought to be possible then to have a look at the bit level of these characters rather than the whole 5 bits together, to try to reveal some periodicity in the patterns of the wheels as they rotate, which is easy to say, but actually to execute is somewhat more difficult, and it amounted to something like 3 months' work before Bill Tutt was able to reveal basically the whole schematic diagram of a machine that none of us on the Allied side get to see until August or so of 1945, the war having, or the European war at least, having finished in May. So this is quite a remarkable feat of advanced engineering. Bill Tutt then went on to deliver his next part of his double whammy, which was an algorithm in 1942 or so, which will give us the ability to find the machine settings that created a particular message. On the assumption we've got an intercepted message, Bill Tutt's algorithm would then give us the ability to reveal the machine settings. And then, assuming we've got our own version of the Lorenz machine, which thanks to Bill Tutt we do have, then we should, in theory, be able to read those messages back. This is purely statistically based analysis as well, so it's pioneering in that respect also. Max Newman is responsible for the mechanization of that process. In 1942, he gets his unit is set up and charged with producing the machinery to speed these processes up, to take a load off, if you like. An algorithm being an algorithm, of course, it can be executed by hand. To use Bill Tutt's algorithm to break a message at the back end of 1942, let's say a typical message of 5,000 characters long, I think you'd be looking at least 6-man weeks for each message. So that's so unwieldy. So Max Newman's mechanization was pretty essential to trying to speed that process up. One of the early products was Heath Robinson, the Robin machine, which we referred to a little while ago. That was plagued with reliability issues, largely down to the fact that we were trying to run two punch paper tapes in perfect synchronism, in other words, effectively mechanically connected to each other. And there's only one way to do that, and that's to synchronize them using the sprocket holes. And any relative movement between the two tapes is going to stress those tiny little holes. The net result is those holes will join up and the tape is in 2 pieces. And it's guaranteed to happen at some point in a run. So this was a permanent plague of Heath Robinson. It wasn't completely abandoned. It found other applications, but it needed to be improved. In early 1943, there was some technology skepticism around, particularly around that newfangled technology, this electronic stuff, valves, vacuum tubes. And this was the uphill struggle that the post office engineer Tommy Flowers faced when he put forward his idea, which we would originally eventually know as Colossus Mark I, in early 1943, spring of 1943. And his proposal was to overcome the reliability issues of Heath Robinson by replacing one of the 2 paper tapes, by a bank of electronics, and the estimate was somewhere around 1,500 vacuum tubes. Given the antipathy towards the use of vacuum tube technology, particularly at that scale, Flowers and had an uphill struggle trying to convince Bletchley Park that could be made reliable. And it wasn't until late spring of that 1943 that finally the green light was given, at least the official green light was given. Flowers by that time had already been able to convince Gordon Radley, his boss down at Dollis Hill, that this was a prospect. Clearly, Gordon Radley had confidence in Tommy Flowers' ability as an electronics expert. And so some early work and design work had already been undertaken by the time the green light came from Bletchley. So effectively, they had start. In terms of trialing, that machine was tested actually in December or so of 1943, which is quite a remarkable development timeline, really, from spring to December of 43. Set that in contrast with things like agile development these days, which is the bee's knees of the development processes and getting things out working really quickly. I've used this as an example with quite a few visitors over the years and pointing them towards agile development and saying, okay, now let's take this as an example. You've got an unknown problem. Scientists, his name is Max Newman, has come to you and said, here's a problem. Basically, here's an equation. I need you to solve this at impossibly fast speeds. And I don't know how you're going to do it, but here's your source material. It comes on a tape, on a punch paper tape. Get on with it. Now, to do that and produce working hardware, which is essentially thought bubble to working hardware in about 9 months, I think it's quite remarkable. But people during wartime seem to do remarkable things. So, that machine, the Colossus one, was tested and proven to be working. The story goes actually that the test in December of that year was so convincing, largely down to the fact it was a fluke. It seems I think it's reasonable to assume that the message was actually quite a short message, which normally wouldn't succumb to the statistical treatment that Bill Tutt's algorithm applies, but on this occasion it did work, and that was a convincing enough demonstration such that machine was shifted up during January of 1944 and ran its first official job on the 5th of February. So that was a red letter day, really. The second Colossus, we think, was delivered in early June of 1944. The story goes, and you'll see it written quite a lot, just in time for D-Day. I'm a bit sceptical about that just-in-time statement. D-Day decision had probably already been taken based upon, apart from anything else, Colossus 1 decrypts and also the plethora of Enigma decrypts that were going on the run-up to making the decision to go on either the 5th or the 6th of June. So it seems unlikely that Colossus 2 had much of an influence over, assuming it was actually producing a product at that time. But no, nonetheless, it was the advent of the Colossus 2, at least we think a Colossus 2. Again, there's no hard and fast evidence to that. We know what the delivery time schedules were because the post office diaries have told us that. But so essentially there's some question about whether it really was a 2 or not. What we do know is that all the machines were brought up to Mark II status. The Mark II is a much bigger and much more capable machine. Okay, so here's the challenge. We've got the Lorenz key attachment. I'm not going to try and pronounce that word. Jerry can do that much better than I can. One time I was a German speaker, but I've lost the ability, so I won't do that. So here we've got a machine here, which by contrast, the Enigma has 12 wheels in it. And it comes with its associated teletypewriter, which is actually a US design made under license by the Lorenz company in Berlin. Lorenz actually is a subsidiary of ITT, an American company founded by a couple of expatriate Germans in the USA. So not surprisingly, they're building American equipment under license. I think I'm right in saying this is a teletype 14. Which came in 2 varieties. This is the one with the paper tape. This is its output with the paper tape in old-fashioned telegram format. There was a page printer version of it, I believe, also, which would have had a different arrangement for the printer gubbins on the top here. But it's a pretty much a standard teletypewriter working in the ITA2 alphabet. connected via serial cable to the Lorenz key attachment here. The key attachment then is responsible for producing a cryptographic key, which is then added bit by bit, character by character, in a stream cipher fashion, and producing yourself your ciphertext stream, which is then transmitted by radio. You have an identical machine at the receiving end, which has precisely the same settings and is in perfect synchronism, character-wise synchronism with the originating machine. And therein is a technical challenge. Keeping that synchronization going over quite some distance is almost guaranteed to fail from time to time. And so this will give rise to retransmission requests. But then the human aspect steps in, as it did on the 13th of August 1941, when we had the repeated transmission with the same key settings. We know that the Germans committed that fatal error, not quite on a regular basis, but certainly throughout the duration of the war, they were tending to get lazy from time to time. And as long as we're aware that the same key settings have been used, then we're going to be reading those messages without too much difficulty. Therein lies the problem, and how are you aware whether the key settings have been repeated? In the early stages, a message indicator was sent, which was always 12 digits long, 12 characters long. And so we can surmise from that, we can derive the fact that there are 12 wheels in that machine. And further, we can determine that one of those wheels, like the extreme right-hand wheel here, has 23 starting positions on it, because that particular letter only ever took 23 letters of the alphabet. Latterly, other methods of trying to obfuscate the wheel settings were tried. You kind of look up tables, this sort of thing, but they were to a greater or lesser degree successful. But we were still reading what we call cryptographic depths, in other words, messages sent in depth using the same key settings on a fairly frequent basis throughout the duration. So you don't need any special equipment for that. This is a complex machine, and it actually it dwarfs the Enigma, 3-bit Enigma's complexity of only 159 million possible settings. This dwarfed by the Lorenz key attachment, 12 wheels, each of which with relatively prime starting positions, ranging from 61 on the M1 wheel to 23 on the K5 on the right-hand side here. They're both primes. There are not enough prime numbers to make them all prime. There are 10 primes between 61 and 23. So there are two relative primes, 51 and 26 in there. They don't mess up the scheme, which is actually basically to ensure that this thing will not repeat its situation or its status or its state, the wheels can be in, until all the possible states have been exhausted, which is essentially the least common multiple of those primes and relative primes, which is the product of them in this case, which is 16 million. So in theory, that's the longest message you could transmit before this thing starts to repeat when it's just done. So that's quite a sound being design. Being digital, of course, it's creating ones and zeros. The wheels themselves have a number of cams around the outside, so the same number of cams as there are starting positions. So they're quite big cams on the K5 wheel, 23 cams. They're tiny little cams on the M1 wheel with 61 of them. So this kind of applies some engineering limits to this. You don't really want to make the cams any smaller than that because they're fiddly. And you don't want to go too much below 23, because this wheel's going to have to rotate fast enough to keep up with the bit rate. The smaller the number of cams on there, the faster that wheel's going to have to rotate to keep up with the bit rate. So it's going to be a bit of a nightmare to engineer that. So these are your engineering constraints. There are 501 cams in total, which gives you 6.5 times 10 to the power of 150 possible settings, 2 to the power of 501 basically. Multiply that by 16 million, that's where you get this number on the right-hand side. In theory, and it is very much a theory, it gives you 10 to the power of 170 different settings, which, to set this in context, is bigger than the number of atoms in the universe squared. So you can see why the German High Command was quite happy with this being a secure device. Clearly, you're not going to use all those settings because some of them will be ridiculous, like all zeros or all ones. But even so, impressive, and they fell Lorenz-encrypted for that as being it's complicated, therefore it must be secure. There's a learning point here, which I try to drum to students when they come through. It's never, ever, never rely on complexity for security. You're hiding to nothing if you do. So from that first message, with the first break, the Tiltman break in 1941, our friend Bill Tutt was able to reverse engineer, or at least not on his own, and he would freely admit that in his writings. The whole of the research section assisted with this, but Tutt exposed the theory behind it and the principle, whereby you could decompose the workings of a machine and nobody gets to see until the war's over. And that is actually, interestingly, it's a technique that originated it was published in 1863 by a German mathematician called Friedrich Korzystki, which, so some people know it as a Korzystki method. It's actually originally designed to determine the key length in a Vigenère cipher, which is a letter-orientated substitution cipher. So, strictly speaking, it's not applicable to this, but the principle is applied by Bill Tutt in a novel situation. It's also, and again, citation required here, it seems that is not original idea of Friedrich Korzystki. It would appear to have originated that principle with a chap called Charles Babbage in the early 1840s. You might have heard of him. So maybe that was plagiarism, maybe it wasn't. I'm not going to go into print on that one. On the basis that if Korzystki's descendants are still on, I will take me to call for it. So here's a tunny machine built by the British Post Office. The wheels in a Lorenz machine replicated here by uniselectors, type 1 uniselectors. The eye eagle-eyed, and John, you will have spotted this. These are type 2s. Spotted that? Not if you did. I can see you nodding. They should be type 1s, but okay, there's only so many type 1s out there when you come to rebuild these things. But so the front of it is what's effectively a repurposed manual switchboard. There are 513 sockets, 501 sockets representing the CAN positions, and 12 start positions. So 513 in all. And offshot to the right, here's a teleprinter that's connected to this. So this will work as an encryption or a decryption device. And all I have to do is put the right plugs in the right holes, and then I can just play the message back through it, the intercepted message back through it, and I will read plain German. So all I've got to do now is find out where to put all the plugs in the right holes in 513 sockets. So this is a direct result of Bill Tutt's original part of work. So here we've got our own version of it. Now we're going to find out, first of all, what the 12 start positions were, and then what the 501 sockets were populated throughout the rest of the machine. Sure, we can do that. We're good to go. We can read messages. Cutting it's real short. The first 5 wheels here, the Chi wheels, are the crucial ones we need to know. When you see this machine in operation, you'll see that the Psi wheels down the bottom here, these bottom 5, they are arranged, the TMUs or motor wheels, arrange these to start and stop. Now, on the basis of if you swallow the argument that complexity is good for security, then you think, well, this is great. That's a complicated action. Therefore, it must make this part of the machine really secure. Well, it doesn't, actually, because if you think about what's happening here, is if these move approximately half the time and stay stationary half the time, what you can say is half the time they're repeating the key. That part of the key, this part of the machine, which is effectively treated as a separate encryption machine, is designed almost deliberately to repeat the key, which is bonkers. Quite why that was the case, who knows? We need to get in a time machine and go back and ask the designer. So that means our basic problem really is if we can find the wheel positions of the first 5, then we are nearly home and dry. We can then use a crib or crib dragging technique to try to eliminate the effect of the Psi wheels down here. The Chi wheels here only have 22 million ways of setting them, so our problem is less impossible. See what I did there? It's still impossible. So Bill Tutt's then going to take his decomposition one stage further. And the realization then dawned, actually, that I can exploit the statistics of the German language, which is based around and this is a gross simplification, bigram or letter pair frequencies, and the way they encode in 5 bits. And there's a whole load of information we can go into. I'll be here all night on that one, so I won't go into that too deeply. And what it means is I can actually restrict my analysis not to 5 bits at a time. In other words, all 5 wheel positions. I can look at that pair at a time. And so I can take maybe the first 2, of which there are 1,271 combinations, and then say, okay, we'll then find the wheel positions for those 2, and then extend the analysis to maybe one of the ones I've already found, let's say 2, and then vary number 5, 4, and 3. Sum total is then I've got 1,349 operations to do, not 22 million. And there's always a catch. The catch is that the number of calculations is multiplied by the number of characters in the message you have intercepted. So it's not quite 1,349. For even a short message, it's millions of calculations. Now you can do that by hand. And at the end of 1942, Bill Tuck's given us an algorithm, which you can do by hand. It's going to take you man weeks. So you're going to need to automate that process. Thankfully, that's where Max Newman steps in his organization. So, concentrating on timeline, 1940, we've got the SZ40. Its early incarnation. Colonel John Tiltman, 1941, gives us a break. Bill Tuck steps up here. This is his algorithm written out in very, very simple terms. In 1942, we've got an algorithm. Practically speaking, we haven't got any decent equipment to actually run it. What we do have, though, is our Heath Robinson down here, which is a bit small, the animation to that, but it is running. And hopefully, you can just see the tape is actually running. And here we've got the 2 tapes. Trying to keep themselves in synchronization. And the up, where there's a couple of counts, it's flipping one to the other. And poor hapless Wren has to write the counts down as she sees them go past. And she has to capture them all. She can't miss any. And that could be 1,271. So you can just see the lights flickering down here, flipping the counts. Every loop of the message tape will cause the new count to be achieved. So she's going to write all those numbers down. At some point, those numbers will give us a statistically significant high score. That high score will give us an indication as to the wheel positions that created that high score, and they're the most likely wheel positions in those 2 bit streams, pair at a time. Remember, we're monitoring pair at a time. Our device or our rebuild of the Robinson machine at the museum, we run at a fraction of the target speed, and that's just so we don't have to replace the tape too often. But all too often, the tape breaks like this, and this is unreliable. Step 4, got Tommy Flowers here, 1943, and he's got the uphill struggle that I touched on before. But finally, we've got his ultimate design, and here's a shot of our rebuild. I've got a larger version of this, which we'll have a walk around in a moment. So I won't run that animation right now. But here you can see our rebuilt Colossus in the position where number 9 machine stood during wartime. Okay, so I can move this on. Lorenz process. Again, this is taken from one of the information boards in the Colossus gallery. Is the Newman is responsible for mechanized wheel braking. They look after the Tunney machines. I think they should be IES as a plural. The Colossi, registry for getting information in and out, and then the Super Robinsons, developments of the Robinson machines for grid dragging and the like. That's Block H. Block H only exists for this purpose. Block H didn't exist until May of 1944, where it's quite clear on the run-up to its erection in May of 44 that we're going to run out of space in Block F. Block F had the first 4 Colossus machines and some Robinson machines and some Tunney machines also. So in Block F, it was quite clear it was going to get full up. So Block H, we can truthfully say Block H was the first data processing center, purpose-built processing center. Test tree is kind of broken down here into 3 blocks. So they're wheel braking and setting by hand, largely from depth. So you've got to rely on mistakes being made. They would use, on occasion, a technique that was originated by Alan Turing, who did have a part to play in this, although no part of the engineering of Colossus, for example. But in particular finding wheel braking, which is the cam positions on the Lorenz machine, His method, and I'd refer to the comments made by Bill Tutt on this. It was regarded as more art than science, and not very many people other than Alan Turing could understand what was going on. And so it was pretty much one all your eggs in one basket, the Alan Turing basket, and he was the person that can actually make that work. And Turingismus, I think it was called, and it did rely, to the best I've been able to find out, relied on using debts. So you are relying on a mistake, at least, giving you access to the key stream, and analysing the key stream to find where the wheel braking positions were. The motor wheel braking was done, again, it's just hard work analysis and then finally a decoding machine, which is the tunnel is operated by Lorenz. So a few words about the core Donis Hill team that worked alongside Tommy Flowers. I can't really let things go without at least name-checking some of these people. Your Dot Coombs, Arnold Lynch, who thankfully, when Tony Sale was rebuilding, had pretty sharp memory. You might almost say a photographic recall. He was responsible for the optical reader, which was used both on the Robertson machine and then adapted for use on the Colossus. Chandler Thurlow, fencing behaviour, Broadhurst, firmware, etc. And of course the boss, who had the confidence in Flowers and his team to actually kind of go out on a limb, really, and allow Flowers to actually begin the design of this with no clear go-ahead yet from Bletchley Park. And finally, TRE, Dr. Wynne Williams down the bottom there, who kind of started the process off, really, the mechanization. For all its failures, the Robinson machine did actually prove that there was future in mechanization. And so, again, hats off to Max Newman for also seeing that through. So, overview of the Colossus machines at Bletchley Park. Okay, so in January 44 in F block, we've got 4 machines in all by, I won't actually read that because he's in the way. By September 1940, they're running out of space by 1944. And so between May and September 1944, Block H is built. So it only exists to keep the rain off Colossus. That's the only reason that Block H is there. It is, I'll posit, the world's first purpose-built computer centre. From September 44 onwards, machines 5 and 10 when they're working. And after May 1945, decommissioning begins, more or less. Okay, there's a reason I've said that. Okay, so a timeline. These are from Post Office diaries, which are available on the web. So we can see in January 44, the first official jobs running on the 5th of February. June 1944, early June, probably a Mark II, but we do know that they were all Mark IIs from now on. Next machine, July, August, September. Notice they've been delivered once a month. This is a production line. So that's quite significant. You got monthly deliveries of these machines. Rectangular gadget. This is worth a mention, maybe. This is another Bill Tutt triumph. This gets us over the problem of not being able to understand Alan Turing's method of finding wheel braking, finding the cam positions. It's a derivative, as far as I've been able to find out. It's a user derivative of Bill Tutt's original so-called 1+2 or double delta algorithm, with an adaptation to do a statistical analysis on ciphertext, pure ciphertext, to reveal cam positions. Basically, it's a massive matrix production machine. So, for example, the K1 and the K2 wheels, if you want to find out what the cam positions are, that is effectively a 41 by 31 matrix that the Colossus with the rectangular gadget can produce for you. And it's down then to the operator or a trained person then to take that rectangle and to converge it manually. And essentially, you're providing yourself with the best guess or best estimate and the cam positions along the 41 and 31 axes of that rectangle, that matrix. So we've got 10th machine on 16th of April 1945. And number 9 was operating. That's where our rebuild is on the 1st of May 1945. Final machine delivered in April 45. And then from May, VE Day, taken to pieces, basically. They were kept running, some were kept running for a period of time afterwards in order to support the activities of Nuremberg trials. Was there well, there's an 11th machine in pieces, it says here. Was there a 12th? Don't think we know. It might have been, perhaps. Either way, those 11th and 12th machines were not completed. There were the Super Robinsons, also used for depth searching, cryptographic, and the other machines I've hinted on before. And it's not clear whether these are deliveries or actually in service. The diary is not too clear on what they are, but gives you an idea of the time frame. But the impressive thing is these things are delivered on a regular basis, courtesy of the post office factories in Birmingham, where eventually these things were being produced on a production line basis. There was some support personnel. It's not all just about the equipment. 26 or so cryptographers, 28 engineers, 273 wrens. These are doing the grunt work, the wrens, on a shift basis. 2 of them for Colossus, all supporting 10 kilometers, 3 rubbers and 3 tonnies. Probably underestimates, actually. I'm pretty sure there were more than these numbers. Certainly Robinson and tonnies. But these are from extracts from the general report on Tunney, which was formatted by Tony Sale during his activities in putting all this information together to start the rebuild off. Okay, so what about the rebuild in Block H? How did that all begin? Well, it kind of starts back in 1972, where Professor Brian Randall began badgering the UK government, proper thorn in the side, and so much so that by August 73, a technical description of Colossus 1 by David Hallward was produced, and it doesn't actually expound very much than probably that we already kind of surmised about it, but it was at least a foot in the door. There was a Los Alamos conference in 1976, which a paper was delivered by Brian Randall, and it was at this that the likes of Jonathan Neumann and Mortley and Presper Eckert, for example, were in the audience. And it was Brian Randall's pleasure to inform them of obviously they were the originators of the ENIAC machine, which had been billed as the first digital computer. And it was Brian had the pleasure, or I guess the obscure pleasure of informing them that what they thought was the first machine was in fact the 11th, because there were 10 operating Colossi machines during World War II. Bletchley Park Trust formed in 1992, and by 1993, Tony had got pretty much all the information that was available collated to him. Only a few photographs, fragments of circuit diagrams, which strictly speaking shouldn't have existed. And the project was officially inaugurated, although work was already effectively underway in 94. By 1996, June time, the official switch on of 2 channels of a Mark I machine, commissioned on the site of number 9, was done, and that's commemorated by a plaque in the Colossus Cavern. So that was a significant switch on. Really, though, it was 2 channels of a Mark I, and so it wasn't even a complete Mark I at that time. And so Tony and the team sat down and decided, well, you know what, we may as well go for a Mark II machine. I don't necessarily think at the time they kind of realised that they're in for another 11 years' work. Finally, 2007, the fully fledged Mark II was in operation. Okay, so this is an undertaking that you'll probably never see again. So if you've had the opportunity to see Colossus, drink it in, because you're not going to see another working Colossus machine. Likewise, the bomb machine, that was only 12 years in its construction, or in its reincarnation. Because the difference with the bomb machine, of course, was that all the parts diagrams were available to it for it. So the rebuild team actually knew what they were building. To be fair to them, they didn't know how it all went together because none of the assembly diagrams were provided, but at least they could build all the parts. This was very much an uphill struggle by Tony and the team. Okay, so it's hybrid technology. Vacuum tubes, valves, EF36, EF38, general purpose AF/RF pentodes here. The veritable 807 tetrode, power tetrode here. High-speed relays, 3000 type relays, workhorse, post office 3000 type relay, workhorse, used globally, those sort of things. Reputation for reliability, looked after. And of course, how does it all work? Well, we've got a tape loop here, a single tape. This is the message tape, some form of reader, some logic to combine bit streams, internal bit stream generator. This would have been the second tape on the Robinson machine. So the bit stream combiners, this is where the clever stuff is done. Effectively the built-up algorithm is kind of embedded in this. It's a bit broad to say it's a bit stream combiner. It's doing a lot more than that, really. The output is a counter. I mean, if you really want to be cruel about this machine, you just say, well, it's just a counting machine. But actually, it's a counting machine with a bit more than you might realise at first glance. Then you've got the output control, which is basically thresholding a significant count, a statistically significant count, and controlling the machine so you don't miss anything. So you don't actually control the progress in the machine while the print is operating, because the print is pretty slow relative to the processing done. We're reading this tape loop here at about 5,000 characters a second. So let's have a little walk around Colossus. Hopefully this is going to come to an end to go through. So I don't think the audio will come through, and there's a bit jerky I can see on the screen here. So I'll freeze it at various points. So what we've got here is a programming area. Okay, this array of switches here, this gadget on the front here is to do with wheel braking. That identifies our rebuild as a wheel braking machine. They wouldn't all had this gadget on the front. In fact, actually, there's not much to this gadget at all. What it's doing is effectively replicating a whole load of connections on the rear of the machine. So this just saves the wren having to wear her shoes out, keeping her walking backwards and forwards around the back of the machine. She's got access to the flexibility about moving connections around on this panel at the front when she's doing a wheel braking run, when she's trying to populate a matrix, for example, on a rectangular run. So here's our general programming area, and these red switches down here are the built-up. I like to call this the built-up area. So each horizontal row of these, you can see along here, there are 5. It's 5-bit code, so our data's coming down effectively on this bus, only a 5-bit wide bus. We've got 2 selected here, so this run will probably be running on bits 1 and 2, which will be K1 and K2 wheels on the first long run. And there are 1, 2, 7, 1 combinations of K1 and K2. So our tape, which is a single tape at any one time, although there are 2 tapes on the reader, the next job is preloading. This tape will be running through here. That's going to do 1,271 loops. Each of those loops will be testing a potential value for the first K wheels, the K1 and K2 wheels. So I've selected those 2 here. I've selected this key's down, so I want to count how many zeros I get from this logical process, and I'm going to put those in counter number 1. Counter number 1 is to our left, and we might see that when we come round to full circle. I'll show you that later. There's also a little bit of an area here where we can steer some data around, but the principal area of programming the built-up algorithm, the core of this, is in this area here. You can see I've got 5 of them here. So this is a bit of genius from Tommy Flowers. This tape is running at 5,000 characters a second. That's about 30 miles an hour. If I could run the tape twice as fast, I'll do the whole process in half the time. That's tempting. So why don't I just turn the speed up? Because it's not under any great stress. There's hardly any friction. I'm not pulling it through. There's very light friction on these pulleys, just enough to get to so it doesn't flap around too much. In the gate here where the light's shining through the holes. So it's not under a great deal of stress. The problem is Newton's first law of motion. This tape has mass. It doesn't have very much mass. But as you approach 60 miles an hour, this tight bend round here becomes a problem. The tape will always want to go straight on. And at 60 miles an hour, not much will stop it. It's in tiny little pieces all over the floor. So you can't go anywhere near that because then you'll reload the tape and start the run again. So the safe speed we will run these out in wartime would be 5,000 characters a second. So that's tempting. Bill Tutt's idea, though, well, not Bill Tutt's, Tommy Flower's idea is, let's see if we can do more work for every loop of the tape, because on this area over here, I'm just selecting 2 bits at any one time. There are another 3 bits coming off that tape. They're there, they're being read, but I'm not using them. Let's use them. So actually what it's given us is free ability to choose any number of pairs of combinations. Remember, the algorithm looks at pairs of bits. We can freely choose any number of pairs, any combination of pairs, and do them at the same time. Now, there are ways and ways to do this. You've got flexibility to even do 5 completely different jobs at the same time. In other words, try to find all 5 wheel positions in theory at the same time. It don't actually work quite like that, but keeping it simple. Now, that's not necessarily the most efficient way of doing it, because it's still going to take you 1,271 loops in the tape to do the first 2. Which is going to be on this message that we've got loaded on here, is about 25 minutes. There's a better way of doing that, and that is to do the first job, the long job, in all 5 machines. So effectively what you've got there is nearly a 5 times throughput improvement. It works out actually it's about something like 4.7 times throughput, but it's a useful throughput nonetheless. And you're going to be doing that first pass, the long job, in about, let's say, 5 minutes approximately, as compared to 25 minutes before. Then you can go and use the multiple processing capability to find the other 3 wheel positions simultaneously. And that would amount to, in theory, again, about another 30 seconds of machine time. So crudely, about 5.5 minutes of machine time gets you that job done for the first 5 wheel positions on this message, which is getting on for 6,000 characters long. Now, I reckon by hand, and very crude analysis, is that by hand, that's going to take you probably 6 weeks solid work to do that, to churn through all those calculations by hand. There are millions of calculations going on there. So this is a vast improvement in throughput. Okay, so as we move around the reader, you can see that there's the second part of the bedstead, the next job in line, preloaded. So 2 runs on each job, 2 runs on each machine, 1 loading the next job, 1 actually running the current job. So here we've got our reader. This switch here is our changeover. So that switches between 2 readers, either the near one or the far one. And this is the reader electronics here. We've got an array of photo detectors here. There are 8 of them for each tape. So we're reading the 5 data holes. We're reading a start and a stop indicator that tells the machine where to start and stop. And there's a blank period of about 600 characters, I think, from memory, 100 or so, 130 milliseconds of blank tape to allow a statistical count to stabilize before it's thresholded and detected as being valid or not, or be of interest or not. So that's done on the tape preparation. So we're also reading the sprocket hole. It's a computer, so it's got to have a central clock. Well, does it have to have a central clock? No. Having a central clock would be a bit of a problem, because you then need to synchronize the speed of the tape with some kind of central clock, and that would be a nightmare. So Flower's idea is to derive the clock for the whole machine, synchronization of the machine, from the tape itself. And the sprocket holes are an ideal solution there, because they are there's 1 per character. So that gives you your natural clock. So that's the basic electronics there. Down here is a motorized transformer. This is our nod to reliability. So we bring the heater supply up on the valves gently. About 90 seconds is all it takes. Rather than throw the switch and require these valves to warm up as quickly as possible, the power is brought on over a period of about 90 seconds. Likewise, and it's taken off in about 90 seconds. And that is enough to give us a considerable reliability improvement. Failures of the order of 10 or 12 a year out of 2,420 valves. That's not a bad failure rate. Of course, during wartime, these things were switched on and left running, which is by far the best way to treat them. There is a finite life to them, to valves, but if you can avoid switching them on and off, then that's so much the better. So this is our bit stream combining, and this is modulo 2 arithmetic going on here. Loads of it on the fly. So And there are some shift registers also, which is buffering information as it comes off the tape. So one of the sometimes you'll hear criticism of Colossus, it's got no memory. It does. It has recognizable electronic shift registers. It's also free using flip-flops throughout it. So, and the flip-flop design's been around since the 30s anyway, so that's no big deal. This area here, coming up on us now, these are thyrotron tubes. They're gas-filled triodes, and when they're triggered, they stay triggered. In other words, as long as there's a voltage across them, anode to cathode, they will conduct, a bit like a thyristor. So you could build a light dimmer of these two back to back, and that's one of my ambitions, is to build a light dimmer just for the kicks. But it should work. There's 501 of these, and they're arranged in logical wheels. So from the top of this rack downwards to 41, 31, 29, 26, 23, down to about here. And then the M wheels are modelled, and the S wheels down this side of the rack. So this is our full emulation of a Lorenz machine in these two racks here. It's double-sided. There are tubes on the other side of these. So 501 of those. Power supplies here. These are a nod to safety. These are modern, well, say relatively modern, 70s and 80s. But at least they're not using selenium rectifiers, which have a tendency to burst into flames. So these are much more reliable. There are 7 of these, and each for 50 volts. So you've got plus 200 minus 150 volts. So logic levels of 3.3 volts, for example, on modern day chips, that's pretty medium. We've got some massive logic swings in this thing. They're still ones and zeros, though, even though they're represented by big voltages rather than small ones. So as we move around, so the rack we're looking at here is the thresholding and the counters. These are biquinary counters, so they're counting in a form of 2 out of 5 code. Okay, whoops. And these switches here are our thresholding devices. There are 5 of those, one for each of the 5 channels over here. I've got 5 discrete thresholding arrangements here, so I can set my statistical thresholds to certain levels, and then the printer will kick in whenever a count, and running count will appear on these lamp boards here. Whenever it's exceeded for a particular run, then I'll get a printout of the candidate values for wheel positions. So that's the basis of the machine. Let's move on. The input then, okay, all computers got input, 5-volt punch tape, 5,000 characters a second. That's impossibly fast for the time. I mean, you'd expect to read it at about 5 characters a second. It's optically read, which is quite the advance for its time. Programming switches and patch codes. We could argue, I guess, that the built-up algorithm is microcoded. It's embedded in the hardware, and you're effectively varying the data streams or steering data in different paths towards it. So we can only really say this is a semi-programmable machine. It does not programmed in any kind of stored program arrangement that we'll recognize these days. The output is wheel positions and scores, or it might be a rectangular matrix. It's fairly basic output. What would have been lovely would have been if the output had been plain text, wouldn't it? German plain text? Well, what you're describing there is a Mark III machine, which only exists in my head at the moment. But I've got a pretty good idea how I'd do it. So if I can think this, then I'm pretty sure that Tommy Flowers must have had this thought before now, because there are a bunch of switches on the front of that machine that allows us to span out some dubious sections of message. In other words, eliminate those from the analysis. And that can be a certain number of characters. So start on a particular character, finish on another character, then ignore those as far as the process is concerned. As long as the rest of the message is long enough, you still get a result. Flip that on its head and say, okay, I don't want to ignore those. They're the only ones I want to read. Now move that window down to 1 character. Now shift that window to the beginning of the message. By the time I've done all my analysis on the 12 wheels, my electronic key, which is being generated, remember, by the 501 thyrotrons, is now lined up with the first character in the message. I'm ready to decrypt. So the machine could then just merge those 2 data streams together, and the output then will be a 5-bit character reference. That might be 11000, and that will be an A. Then take the switches and move it along one position. So now I'm lined up with a second character. And the machine will then automatically line up with the second character of the key and merge them together and reveal the second character in plain text. Now that's a pain switching one by one, but you can automate that process, piece of cake. So what you're going to get then for every loop of the tape is a fresh, decrypted plain text character. Now you might argue that's quite slow because the tape running maybe on this particular, on the run you saw there, that's probably going to be printing one character every second, which is pretty slow. But the thing is, think about what you're saving. You're saving the ability, the necessity to take wheel positions, walk them next door, plug them up on the toning machine, and then pump some poor Ren in front of a typewriter. So now type 5 or 6,000 characters. And oh, by the way, don't miss any out. Otherwise, you get out of step. So, or if you're lucky, you might be able to feed a pre-prepared tape in, but have a word with John Pether about that, as whether he thinks it's likely that they could ever get those toning machines to work on tape. And he'll furrow his brow and say, probably not. So we have some doubts about whether they could actually take data at that kind of rate. Maybe they did, but we've not been able to. We're sceptical about that, let's put it that way. So the Mark III machine, I think, would have been doing the bee's knees. But of course, the war finished, so no need to take the design any further. So was it the first? Well, you'll see it was the first computer. No, it wasn't really the first, because Konrad Zuse probably takes that, or does he? 1940, his relay-based machine, which is recognised to be a computer. No, it wasn't the first. Is it general purpose? No, but... okay. Is it large scale? Oh, hell yes. Look, 2,420 mils, so definitely yes. Is it electronic? Yes. Albeit it's hybrid. It's hybrid for a reason. All this stuff here, which is staticizing those statistical counts, is there for a reason. It's pragmatic design. This hybrid design means that Flowers and his team don't have to worry. This doesn't have to operate fast. This fast stuff is on the right-hand side here. All this processing over here has to be done quickly on the fly. Here, we've got not time to waste, but we've got time to play with. So when we're storing the result, that can be stored on a bunch of relays. It's no need to make that fast. It doesn't need development time. These are standard off-the-shelf relay sets, and they can be wired up in the factory. So this is pragmatic design for my book. So it doesn't need to be fast. So it is hybrid, but all the fast stuff is being done electronically and in ones and zeros, in valve technology. It's digital, yes. It's reliable, yes. Mass produced, yes. So it's the first if you apply all these caveats, all these qualifiers to it. Okay, so we can safe to say it's the first large-scale electronic, digital, reliable, mass-produced computer for sure. It is a computer, but it's a single-purpose machine. Single-purpose. It's multi-purpose in that there are at least two things you need to know about a Lorenz machine. You need to learn the start positions of the wheels and also the cannon position. So it's pushing it to call it multi-purpose, but it's all concerned with finding Lorenz machine positions. So there's some legacy to this. And as we're on anniversaries, this kind of converges really. Here's Max Newman. In late 1945, he became field and professor of mathematics at the University of Manchester. And he and his team, which eventually contained also, he prized Alan Turing, came along to work for his erstwhile tutor at Cambridge, can claim to be the first stored program computer. This is the Manchester Baby, more correctly, the small-scale experimental machine, which ran its first program in 1948. Ironically, this is before anybody's built a stored program computer, which follows the von Neumann architecture. So this is very much a first for the UK. This becomes the Manchester Mark I for academic purposes, which is then commercialised by Ferranti, referred to over here, the Ferranti Mark I, available to buy in 1951, the first commercially available general-purpose computer. Okay, so the Ferranti Mark I, through its evolution and through various mergers and acquisitions, can point its its heritage, together with EDSAC and all those other foundation technologies, up to 2024, where we've got our ICL 2900 series just celebrating in 2024 its 50th anniversary. And here's our 2966 in the museum, a working bit of kit here. So there's some interesting kind of juxtapositions here. So according to CCS, Computer Conservation Society, there are 2,900 still out there doing useful work. Again, citation required on that because that's just a statement from CCS. But even so this the legacy from Colossus is the inspiration. I would say is the inspiration for Max Newman to have confidence in putting forward what would have appeared to be, with skepticism around vacuum tube technology, a no-go. I've also, there is a memo that highlights the fact that Max Newman took with him 2 Colossus racks with his next employment. Now, clearly, he wouldn't have been able to say what they were used for, but what they would have served for is an illustration of large-scale use of valve technology. So likely they were 2 of the counter racks, which are quite highly populated with vacuum tubes. So if you're trying to put forward a proposal to build a machine, or better convincing hardware, say, look, this can't tell you what this did, guys, but this was, look at the scale of this thing. And actually the real machine had several more of these racks, considerably more racks, and it worked fine. So maybe or maybe not that swung the deal on Manchester Baby, but it's nice to think it perhaps did. So the Colossus itself, other than the fact it was an early statistical attack, zero knowledge attack on a cipher system, its single-purpose technology doesn't really project into the future. So, but the principle behind large-scale electronics sure does. So that's what I would say, at least. So legacy on the H-Block's art, and Bletchley Park in particular, is it was the world's first purpose-built computer center, data processing center, call it what you will. So H-Block has a future. Became used for teacher training, 1948, 1950, also taken over by the GPO for training. F-Block was demolished in 1987. It was in pretty poor state and ready to fall down. GPO engineers in 1956 went on to design this. You can see this is a rebuild of the prototype for Ernie, only a 2-digit random number generator, but its connection, of course, to Colossus, and the fact it's in the Colossus gallery, is it's flowers and these people that have designed this thing. So that's their kind of wartime civvy street work. Interesting, and then this is one that then fed me the other night, and I'm not going to go into so much detail on this because this probably needs looking into. For a time, G&D Block may well have become, briefly at least, the capital of UK-controlled Germany post-war. Certainly, a chap called Charles Brandreth, who was employed at that time by the Allied Control Council, which was effectively a quadripartite arrangement of people who were going to look after basically the fortunes of Germany post-war. And briefly, at least, before it was relocated out to Germany itself, Brandreth, who is the father of Charles Brandreth, the celebrity, let's call him a celebrity. So it's a quirky little story about the Bletchley Park, the legacy, if you like. And all of the Cold War. Well, I'll leave you on that one a bit hanging a bit, really, because I'd need to refer you then to another YouTube presentation, which is on our YouTube site, that was done by Jerry and I a few months ago, where we surmised, well, hang on a second, why were 2 of the machines? We know that 2 of the Colossus machines were not dismantled. Numbers 9 and 10 became designated red and blue at the end of the war. Is it reasonable to assume they had a lifetime after the event? Well, why? Because the Germans now are in defeat. Who's using Lorenz machines? It's only good for Lorenz machines. Well, who got to Berlin first, I suppose, is the next question you'd ask yourself. And the obvious answer to that is, well, whoever got to Berlin first was certainly not the Brits and the Americans. We were preceded by some weeks by by the Russians, or the USSR as it was then. So reasonable to assume the USSR may have pressed these things into service, but then, of course, does this work? Does the statistical feature work that Bill Tutt's algorithm exploits? And the answer is, well, cut a long story short, yes, it does. And so Colossus could well have been used to decrypt Russian encrypted traffic during Cold War. Now, intuitively, you say, well, on the balance, probably not, because the Cyrillic alphabet is different for starters to the Roman alphabet. But only one way to find that out, and props to Jerry for doing all the hard work and doing the maths behind that and proving it does. So, with that, I'll leave you. If there are any questions, I will attempt to field them, but I see there are 2 or 3 people on here who are probably better able than I am to field questions. But I see we've run by about nearly 20 minutes. But hope you found that interesting. Inspired, if you've not been to the museum, do come and see it, because it's unique. It's a great place, and so the people that work down there, they're fantastic. So it's the best job I ever had, that's for sure. And I've spent a long time in the post office and BT as well. So it's kind of not quite like being back home. I did have some work to do in Faulkner House, which was demolished in the 1990s, I think, to make way for housing. But I never actually had the opportunity to work in Block H, other than now. So over to you, folks. Any questions? Well, thank you. I don't actually see any questions, so I could think. Jerry or Len, do you want to add anything to what I've said?
Well, I would add that apparently there's a piece of the blue Colossus has appeared in our pop-up exhibition room.
Oh, yes. Well, that's interesting. Yes.
I don't know where it came from, but
yeah.
How we got it.
Well, I'm probably speaking out of turn, but there is a piece of either red or blue that's on our working Colossus as well. You're not allowed to say how it got there. But I don't know whether the Trigger's broom principle applies, and we can call it an original Colossus simply because it got one original component on it. But what I like to think of is there's a 50-50 chance it's back where it started, because it would have originated either in number 9 or number 10. And so that's quite nice. But yeah, there is a new display about the Colossus, and there's some interesting audio clips of people who worked on the design. So it is worth a visit to the museum just to listen to those, for sure. Anything else? Len, did you want to say anything about?
Well, looking at the Colossus, is that a Fried and Flexo lighter still on the front?
It is, yeah. This is not contemporary. That's 1950s. The thing is, what we really love, and maybe I should put this plea out here. If anybody has an IBM Electro writer, looking around anywhere, these things are usually about a hen's teeth. We'd certainly love one of those, because that would have been the device that was on them. The contemporary device. But they're really quite hard to come by. It's just standard ITA2 output. There's nothing special about the format that it takes, but certainly it works as well as, but it's not strictly speaking correct. So good, well pointed, well spotted.
I've got old IBM typewriters which had the, before the golf balls, electrical inputs.
Yeah.
But I don't know how old they are.
If it's 1940s vintage, I think we'd be interested. But
well, no, it wouldn't be that. It would be probably 60s, something like that. It was the old type where you have the hammers come up and hit the paper.
Oh, yeah. No, it would have been, and so is this one. But
Yes, but wouldn't an IBM one be better than a Frightened one? Should look more original.
It would look more, I suppose it would look more appropriate, yeah. Even so, this does work, and it's rare that we actually, in fact, I've only ever seen it working on video, and I've been volunteering for the best part of 11 years now. So I've never actually seen this physically in operation, but I'm told that it's pretty flaky. And after only a short period of work, it needs to be kind of almost dismantled and reassembled before it work again. So, yeah.
And of course, there was a a modern oscilloscope lurking in your tour around.
Yeah, we've got an old ultrascope which is sitting on the floor.
There's one halfway where part of the optical reader monitoring something or other.
Oh, that wasn't. Yeah, that's an old. I think it's it's the old equivalent of a Techscope. Yeah. Now that's obviously not contemporary, but that's just to show. Actually, what we're trying to show there is the quality of the clock really that comes off. It's a really stable clock that comes off that tape. Reading it off at 5,000 characters a second, reading the sprocket holes, it's a very, very stable clock. And that in itself, I think, is quite remarkable. So that's the reason that's there. But we have got a contemporary scope that's sitting on the floor that I think works. I think from memory, it's got it seems to have a blue tinted trace on it as well, right?
I think that's the Colossus 339s.
I think it's a Colossus, or it might be an Ultra. I'm not sure.
The Colossus 339s.
Yeah.
There is probably a blue with an orange.
I think it's from memory it's a blue, but
most of those 339s with a blue trace have an orange afterglow, so you can see sort of in a semi-storage scope.
Colour TV before colour TV.
Yes.
And if there are any other questions, then I'll bid you a farewell.